D'accord. Merci. Ouais. Ah, ok. Bon, maintenant, ça a l'air de marcher. Super, merci. David, the presentation will probably take 50 minutes more rather than 45.
No worries.
I'll try my best. I start to share my screen, maybe, so that.
Shall we start then?
Let me just check. Yes, it works. You tell me when I can start. Huh?
All right, so good morning, everyone. We are all gathered here virtually to see the presentation that Paola Di Matteo is going to make.
Maybe so that.
You can eventually award the diploma of habilitation dirigée des recherches, which is the highest diploma awarded by a higher education institution. So this defense will take place.
You tell me when I can start. Huh?
All right, so good morning, everyone. We are all gathered here virtually to see the presentation that Paola Di Matteo is going to make. You can eventually award the diploma of habilitation dirigée des recherches, which is the highest diploma awarded by a higher education institution. So this defense will take place.
You tell me when I can start.
All right, so good morning, everyone. We are all gathered here virtually. I think there's a problem with having several. You can eventually award the diploma of habilitation dirigée des recherches, which is the highest diploma awarded by a higher education institution. So this defense will take place.
You tell me when I can start.
Right. Good morning, everyone. We are all gathered here. Several. You can eventually award the diploma of habilitation dirigée des recherches, which is the
So good morning, everybody. So thank you for being here. So I'm going to present in the next 45 minutes or so the work that we have been doing in collaboration with many people, as you will see later, on the modeling of the Milky Way in this wonderful era that is the Gaia era. So if we want to describe very briefly what the Milky Way is, we would say that it's a disk spiral galaxy with a bar in its center. And so in the Hubble classification scheme, it would probably be between the SDB and SDC type. And you see schematically the main features and the main components of the Milky Way in this plot on the top.
Where you see we don't see your presentation.
Oh.
We just see the first line.
You don't see it?
No, yes.
Strange. Okay. So in this plot on the top, you see a schematic representation of the Milky Way with the bulge in the center, a thin disk, and then a vertical thicker component that is known as the thick disk of the galaxy. And then here, these are the places where most of the stellar mass of the Milky Way is. And then there is this very faint stellar halo that surrounds the disk and the bulge, and where many of the metal poor stars in the galaxy are found. Now, this schematic in representation and these different components that make our galaxies are not peculiar at at all. The bulge, as we will see, has a boxy peanut-shaped structure which is not rare. In fact, about 40% of bulges in the local universe have this morphology. And also the presence of a thin and a thick disk is common among these galaxies of all morphological type, from lenticulars to late type spirals. And also the stellar halo, which is in this image on the top, seems a smooth component, but in fact it's not at all smooth. There are plenty of structures in the halo. And also the fact that this halo, the stellar halo, is structured is something that is common also to many other galaxies. And it's of course a signature that ongoing accretion events are still happening. Now, these structures are not rare, and moreover, if we look at the total stellar mass of the Milky Way, it happens to be of about 5×10 to the 10 solar masses, and most of the stellar mass in the local universe resides in galaxies that have similar masses. So, understanding the Milky Way and its component, beside the interest that can have, because we want to understand the galaxy we live in, but it's also an importance to understand how these galaxies like the Milky Way can have been formed and evolved during time. Now, all the discussions and results that I will present about the galaxy have been framed even before the release of the different Gaia catalogs, but they have been framed by the fact that this mission was about to be launched, and then to deliver the wonderful data that is given to the community. So on the one side, we have the Gaia data with parallaxes, proper motions, radial velocities for a subset of stars. And on the other side, we have many spectroscopic starbase that are complementing Gaia with radial velocities and stellar abundances. And this is giving us a wonderful opportunity to really understand all the links between the different structures that I was showing before, between the stellar halo, for example, and the disk, between the bulge and the halo, between the disk and the more metal pura and the most metal pura population in the galaxy. So I'll try to go through some of these discoveries and how we contributed to understand some of these links between stellar populations in the galaxies. And we will see also that on the one side, we need to understand the data, and then we also need to have models that can help interpreting what we are finding in the data, and also eventually to anticipate new discoveries. So I will start by discussing a little bit the bulge of the Milky Way, that is the central overdensity that we see at about longitudes less than 10 degrees. And latitudes less than 10 degrees and longitudes less than about 12 in the central part of the galaxy. Until the beginning of the 90s, the bulge of the Milky Way was considered to be a structure and a population formed in some sense independently from the surrounding disk. It was seen like a sort of small ellipticals sitting in the middle of the disk. However, at the end of the 80s, there started to be a number of results showing that probably the situation was a bit more complex. On the one side, we were starting to have data showing that many these galaxies had bulges in the center, which didn't have really a spheroidal shape, but rather a boxy peanut shape, as you see in these first works by De Souza and Dos Anjos on the left. And then we started to have the first 3D simulations, some snapshots are shown in the right, showing that it was possible to form these boxy peanut-shaped structures as a simple evolution.
We don't see the slide. You're still stuck on slide number 2.
Oh.
Well, I suggest you say which slide you are, and we follow up here with the PDF.
Oh, sorry. So I'm at slide number 8 now.
Yeah, but try again to upload.
So you want me to disconnect, to stop share and share again?
Yes,
maybe yes.
Up. You see moving the slide now?
Try to move now.
Okay. Okay.
This is good.
Okay, sorry for this. So yes, so we started to see these boxy peanut structures in the data, and also the first 3D simulations and body simulations were starting to show how it was possible to form these structures simply from material coming out from the disk through bar formation and instabilities. And some decades later, now we have a clear 3D view and representation of the bulge of the Milky Way. It is in fact the thickest part of a bar that is elongated of about 5 kpc from the galactic center, which has an orientation between 28 and 33 degrees with respect to the sun center of the galaxy line of sight. And if it was possible to really observe the bulge from an angle perpendicular to the bar major axis, we would clearly see its boxy peanut shape that is partly hidden by the orientation of the bar. So this on the observational side. On the modeling part, we now, after several decades of n-body models, we have understood how these structures form, and they often are associated to global instabilities that can occur in the central regions of bar galaxies. And the takeaway message from all this is to understand that when we see a boxy peanut morphology in a bulge of a galaxy, this is a direct indication that at least part of the material in this bulge is coming from the disk. So it's a strong link, it's a strong evidence of the link with the disk populations. So if the global view was clear, some years ago there started to be, already about 10 years ago, a number of results showing that there was in any way some complexity in the bulge that was not only related to the morphology. And this appeared clear when we started to look, for example, at metallicity kinematic relations that were indicating that, for example, stars with different metallicities in the bulge do not all share necessarily the same velocity dispersions, or that stars with different metallicities tend to describe a different peanut-shaped morphology, or also that the content of metal-poor and metal-rich stars change with the latitude and the distance from the midplane. So we wanted to investigate, we started to investigate in this context whether a disk scenario for the formation of the bulge was able to reproduce the trends that we were seeing in observations, like, for example, coming from the Argos surveys or Bulge. And so in the following, I will show only a few of the results. So the first step was to try to show what the bulge could not be, in the sense that the first step one can take is to imagine that, for example, the bulge can be the result of a boxy peanut shape structure plus a classical bulge. And then the classical bulge can be responsible, for example, to the metal population. And we showed already that this could not be the case, because in that case we wouldn't have matched the chemokinematic relations that we were finding with that the Argos survey was finding. Another point was to show that the bulge could not be only the result of stars formed in a thin disk and then mapped into the boxy bulge. And so for this, we ran several n-body models to show how stars from a thin disk can be trapped into the bulge bar instability, and to show that even if we include a steep metallicity gradient initially in the disk of the Milky Way progenitor, so that the most metal poor populations can be mapped also into the boxy bulge, the result was not consistent with what we're finding in the data. And here you have an example on the right of what I want to say. If all the material, or most of the material that we see in the bulge of the Milky Way, was related to only thin populations, thin disk populations, what we should observe is a tendency of increasing rotational velocities for stars in the bulge with decreasing metallicity. That is something that we don't see in the data. We see that the cylindrical rotation is essentially the same for stars of different metallicities. So clearly, this was indicating that if we imagine the bulge simply as the result of an instability occurring in a single component disk, this cannot tell us the whole story. And so we started to look around the bulge, and at the time there were several new results coming out for the disk of the Milky Way. In particular, on the disk side, we were learning that the disk was vertically structured, something that we already knew, but we started to understand that the metal poor populations of the disk were dominant in the inner disk of the Milky Way. And we were also putting constraints on the mass, total stellar mass, that must have been associated to this metal poor and metal rich population. So we tried to summarize all these in n-body models that this time were taking into account multi-component disks. So with metal poor and metal rich populations, we initially should have a different kinematics, hot for the metal poor population, like what we see today in the thick disk, and cold kinematics for the most metal rich ones. And when we started to run and analyze these models, we saw that we were finding the same tendencies we were finding in the data. That is, for example, as you see here on the left, that the contribution of metal-rich population to the bulge should be dominant close to the galaxy midplane and should decrease as we go further out, that the contribution of the most metal-poor population should be opposite, that is, it should increase with the distance from the midplane, while there would be a bulk of intermediate metallicity stars that should be visible at similar with similar percentage at different distances from the plane. And this was very in agreement with what surveys like Argos were finding. Now, a strong constraint came also with the publication of the Apogee DR14, because at the time we had Francesca Frangudi, who joined, in fact, our group and really gave a big contribution in understanding and deciphering the nature of this Milky Way bulge. And what you see here is a metallicity map of the bulge region and the surrounding disk taken from Apogee. And one of the things that you can see is that there is a vertical metallicity gradient, that is that most metal poor stars are found on average at higher latitudes above the plane, but you can also see that stars in the surrounding disk are more metal rich than stars in the bulge on average. And this was something that a model which takes into account an initial vertical structuring of the disk was able to reproduce in an impressive way. Here you can see the results of an n-body model compared with the Apogee data, and you can see exactly the same trend. And we found another strong indication that this vertical structure in the disk must be fundamental to understand then the bulge. Because in fact, when we compared the metallicity gradients that we would expect in the bulge in two different scenarios, a scenario that here is called M2, where the model has initially only a thin disk and a very steep gradient, as it was suggested in the literature, with a model where on the opposite, there is a vertical structuring, but there is no radial dependence of the metallicity gradient. You see that the two models give two different answers. For example, the solid line, which corresponds to the models we were developing and working on, can reproduce very nicely here at different latitudes what we observe in the Apogee. You can see the same trends. So the Apogee data are the points, while the solid lines corresponds to these models. If you compare these with models like those, for example, suggested by Martinez, Valcuesta, and Gerhardt in the same years, where the metallicity distribution that we see in the bulge should be simply the results of a mapping of a thin disk into the bulge, you see that the expectations are quite opposite, especially for the trends with longitudes, with what we observe. So we learned two things essentially, that the bulge in fact contains really fundamental indications about the properties of the disk at the time of the bar formation. So we can use the bulge and the properties of the bulge nowadays to constrain to what is made of, but also really to try to derive information about the properties of the surrounding disk at the time this structure was in place. And in particular, that it was really important to take into account this vertical structure of the disk, the metal poor and kinematically hot population, the thick disk, and the more metal-rich and kinematically colder the thin disk, to understand what we are observing. Now, so all this work led us to clearly understand that there is a strong link between the bulge and the surrounding disk. If we want to understand the bulge, we need to really, we are right to conclude that in fact most of the bulge has a disk origin. And at the same time, one can answer also, one wants also to try to answer the opposite question. Is there any signature in the disk of the bulge, of the bar, or the formation of the bar and the bulge? And can we find in the disk also traces of the bar temporal evolution? And these are not a simple answer. So this work is ongoing, and it's something that is, of course, of interest for many groups which do research in this field. But one of the approaches we try to follow was the following. So a few years ago, analyzing a sample of stars at the solar vicinity, in a paper led by Misha Haywood, what we show was that, and this is the plot on the left, that stars at the solar vicinity satisfy a very tight relation relating the alpha over iron abundance of the stars with their ages. There is a first steep part of the relation that is made of stars which are older than 8-9 billion years, and then there is a flatter part of the relation for stars that were formed in the disk in the last 8 billion years. So because alpha over iron ratios, we know that are really clocks of the star formation and of the chemical enrichment in the galaxies, we try to understand what was the star formation history that was behind this relation. And so with the help of Owen Snaith, between 2014 and 2015, he led really a huge work to try to implement a chemical evolution model to try to answer to the following question: what is the star formation history that can reproduce this alpha over iron age relation? And we ended up with the star formation history that is shown here on the right, and we shows that essentially the galaxy experienced a strong or an intense phase of star formation in the first 3-4 billion years of its evolution, and there is a second phase of more quiescent star formation that started about 8 billion years ago. But in between these two phases, there is a very rapid decrease in the star formation of about a factor of 10, if then one has to take into account the uncertainties in the star formation rate, in about 1 billion years. What we called a quenching, a rapid decrease of star formation. And one of the questions was what can be the cause of this rapid decrease in the star formation that we observed in the galaxy from stars at the solar vicinity. So before answering this question, I would like to say that even if this work started only looking at stars at the solar vicinity, what we realized is that this quenching is really a feature of all stars in the inner galaxy and in the bulge. And the signature of this quenching episode are in fact imprinted in the alpha over iron distribution of stars. So we used apogee stars and we looked at their alpha over iron distribution, as you see here in these panels at different distances from the sun. This is the solar vicinity, and then we go to the innermost region of the disk, and also bulge. And in all cases, we see this bimodality. And this bimodality in the alpha over iron abundance is really a signature of the quenching episode experienced by the Milky Way. So we see this quenching all over the inner disk. We see it in the bulge, which is also another signature of the link, the tight link between the bulge and the disk population. And one question was, what can be the cause of this quenching? So just to come back one moment to this figure, you see that essentially this quenching happens in the last started about 10 years ago, and it ended about redshift 1. And we thought that this was interesting because we know that in many galaxies as massive as the Milky Way, we see the appearance of bars around redshift 1. So we wanted to understand whether there can be a causal link between the formation of bars in these galaxies and a decrease in the star formation rate. And so this was a work that was initiated by Sergei Koperskov when he joined our group with a postdoctoral position some years ago. And for this work, what we did was to run a number of controlled simulations where we were imposing the potential and the characteristic of the bar in terms of strength, in terms of time of formation, and then some full and body models. And in both cases, what we found is summarized here on the right. You can see here in black a model where the disk doesn't develop any bar. So you see a star formation rate that increases in the first 100 million years, and then that is essentially constant or simply slowly decreasing. But if a bar forms, depending on the strength of the bar and depending on the formation scale of the bar, how rapidly this bar forms, you can see a clear decrease in the star formation rate. And depending on the characteristic of the bar, this decrease in the star formation rate could be comparable to that we were finding in the Milky Way. And so simply to appreciate a bit differently these results, what you see in these panels are the distribution of stars in the simulation, where we look at the Kennigat-Schmidt plane. So here you have the density of the star formation rate as a function of the gas density. And what you see is that when you look at the whole disk, in the case of a disk without any asymmetry like the central bar, you see essentially that everything is redistributed along the Kennigat-Schmidt law. And here you can see how this relation is for different radial intervals in the disk, from the innermost part to the outermost part. But if a bar is present, you can see how things change. And in particular, you can see that there is this drop in the star formation efficiency in the central regions. So the drop is mostly seen really in the innermost region of the disk inside 5 kpc, which coincides more or less to the length of the bar in these simulations. So you see that there is still plenty of gas in this simulation because the sigma gas is high, but this gas is not able to efficiently be converted into stars. And the reason for this lower efficiency in the star formation rate, we think can be understood looking at the panels on the bottom, where this relation is now color-coded by the gas velocity dispersion. And what you see is that what's happening is that in the central regions, the gas velocity dispersion now, where the bar is, are much higher than in the surrounding disk. So we associated this high velocity dispersion of the gas to the gas streaming motions along the bar that should prevent, in fact, an efficient enough star formation. And you can see that in the case where there is no bar, we don't see at all this kind of effect in the central region. So a possible imprint of the formation time of the bar can be in the quenching of the star formation in the galaxy. Of course, this is not necessarily the only mechanism and the mechanism which worked for our galaxy, but it's interesting to explore it, to understand how it can also be related to other possible scenarios. Another possible imprint is maybe found in the kinematics of stars at the solar vicinity. So as you all know, there was this beautiful discovery that came out soon after the release of the Gaia DR2 data, which consists in made by Teresa Antoja and collaborators. So what they looked at was at the kinematics of stars at the solar vicinity, and thanks to the wonderful quality of the Gaia data, it was possible to show that the existence of these what are called these phase space spirals, that is in a plane that where we plot the vertical velocity the vertical velocity of stars as a function of their distance above and below the plane. What we can see is that the distribution of stars is not smooth, but there is a kind of spiral-like feature that is more evident if we plot the stars according to their radial velocity or their azimuthal velocities. And the consequence of this interpretation of this finding was that, in fact, the galaxy, at least the disk at the solar vicinity, is still phase mixing, and it has been probably perturbed in the recent past by some events. And here you can see a kind of a schematic representation of the large-scale view of these phase-space spirals with the disk oscillating. So what is the cause of these perturbations and these oscillations that we see at the solar vicinity? One of the possibilities that it was already suggested by Antoja and collaborators, and that has been analyzed in many other papers, is that this perturbation in the disk is recent, and it probably happened between 300 and 900 million years ago, and it's possibly associated to sorry, now all the animations I have to, and it's possible associated to the passage, the last passage of the Sagittarius dwarf galaxies along the disk. So the last passage of Sagittarius should be responsible in this scenario of the perturbation that we see in the kinematics of stars. Now, this is a scenario that is, of course, under investigation. There are debates about whether the current mass of Sagittarius can really be enough to explain the strength of the perturbation that we see. And with Sergei Koperskov, we decided to, we started to look at another possible scenario that instead of requiring external perturbations is more related to the internal perturbation, and in particular, again, to the bulge and its boxy peanut nature. So our question was to try to understand when a bulge like ours forms, and we know that this boxy peanut shape is often the result of a buckling instability, how this buckling instability, does this instability leaves some imprint also in the disk, and if so, for how long? So we ran some very high resolution and body simulations because we needed to resolve with enough stars also the solar vicinities in our simulation. And what we showed is that this kind of buckling instability, in fact, can generate perturbation that can propagate in the disk for several billion years. And you can see here this kind of perturbation and wave-like propagation in the disk at different radii. And so if I can, I just want to show you a little movie of this. I'm not sure it will work now with this. Okay, so for this, as I was saying, we ran a simulation with more than 140 million particles in the disk of this Milky Way type galaxy. And what you see here is the disk initially seen face on, so the stellar disk initially face on. We see it now edge on. At some point, we will start to see, okay, this boxy peanut structure in the middle. I'm sorry, I don't control now the speed of the animation, so I have to let it go as it is. And soon now you will start to see again a face-on map where the color now indicates in fact bending modes essentially in the disk. So the positive, the red and blue colors corresponds to this propagation of the wave in the disk. And if you compare the model prediction for a solar vicinity volume on the right with the phase space spirals seen by Gaia, you can see that there is a very nice qualitative agreement between the two. Of course, this discussion is completely open. What is the origin of this perturbation? It can well be a mix of the two, but it's nice to think eventually that there is some echo of this bar buckling also that can be found at the solar vicinity also several billion years after it happened. Now, the results I was showing you before are linked to the initial phase, the initial epochs of formation of the bar around the bulge. But as we know, bars can, in fact, generate secular evolution in galaxies. And one of the another point that is highly debated in the community is, of course, associated to radial migration. So how and if stars can change their birth radii, and what is the impact of this change of guiding radii of stars, for example, in our understanding of the chemical distribution of stars. So if we take a bar pattern, so we have been in particular interested in studying the impact of the bar on this migration and redistribution of stars. And we know that if we take a bar pattern, a bar with a constant pattern speed, stars can be locked at the associated resonances. Here, for example, you have a plot by Severino and Clipping from an N-body model showing stars that are locked at the co-rotation of the bar. And as they show very nicely, if the pattern speed doesn't change, that is constant with time, stars locked at resonances will oscillate. So their angular momentum or their guiding radius will oscillate between a minimum and a maximum value, but the average value will stay constant. So we started to explore cases where, in fact, the pattern speed changes with time, and in particular, what happens when the pattern speed decreases with time. And these are works that have been led by Anna Lallet during an ATOR position with us. And so what we did was to run or analyze N-body simulations of single of multi-component disks, really looking at the effect of these stars that are trapped at resonances when the resonances move throughout the disk. So here you can see, for example, the results of some test particle integration, where an L shows the orbits of stars for a star that is locked at resonance and the pattern speed is fixed. And here on the middle row, you can see what happens when, for example, a star stays locked at the co-rotation resonance, but the co-rotation resonance move outwards. So the star can, of course, migrate for several kpc from its initial birth radius. It's a work that is ongoing because there are, of course, plenty of parameters to take into account in this kind of studies: the strength of the bar, how the redistribution of angular momentum between the bar, the disk, and the dark matter halo. But one of the first application and of course, one of the long-term aim of goal of this work is to try to understand whether this trapping of stars at resonances with resonance that move in the disk can in some sense be related, can explain or can explain the characteristics that we see in the distribution of chemical abundances in the disk, and that are summarized in this plot by Hayden et al. 2015, who analyzed apogee data and showed that clearly the chemical patterns in the inner disk of the galaxy that are shown here differ from the chemical patterns in the outer disk. So at the end, what we would like to understand is whether the bar and the resonances of the bar has something to do with these different patterns that we see in the inner and outer disk, if they were responsible to set these patterns in the galaxies, or whether they have been responsible to maintain these patterns once they formed. So a first application of all these questions comes from the study of very metal-rich stars at the solar vicinity, what they were called super metal-rich stars already in Grenon studies in the 70s. So here we are talking of stars with metallicities above 0.2, 0.3 dex, and some of them are found at solar vicinity on low eccentric orbits. By low eccentricity, I mean lower than 0.2. And so the question is why can we find these stars here? Because the metallicity is clearly higher than the metallicity of the star-forming regions at the solar vicinity. So already Grenon in the 70s suggested that possibly these stars are coming from the inner disk, but how did they reach the solar vicinity? So a possibility that we wanted to study and explore further is that these stars, in fact, were locked at the resonances of the bar, and then with the bar slowing down, they could reach the solar vicinities and be deposited there. And in fact, you can see that these stars are really, you see many of these metal-rich stars in the inner disk, while as you go further out in the disk, for example, in the outermost radial bin in this plot, you see that essentially there are only very, very few of these. So, and for this, we ran we analyzed some n-body simulations again, where we started to look in particular, because one of the debated point was about the eccentricity. If the stars are locked at resonances and were initially really in the bar regions, is it possible that they reach the solar vicinity with such low eccentricities? And the short and quick answer is yes, it is possible. And in a work led by Sergei Koperskov, what we showed is indeed that these stars can have been followed, the co-rotation or the outer lingular resonance, and as the bar move, as the pattern speed of the bar diminishes and the resonances move out, and the bar strength diminishes, some of these stars can leave the resonance because the bar is not anymore strong enough to maintain all these stars locked at the resonance, can leave the resonance and start to circularize their orbit. And this is shown in these panels for different orbits. You see the blue colors correspond to the early times of the simulation of the evolution, where you see that these orbits are clearly elongated and eccentric, but then as the stars move out, in fact, their orbit can be circularized. So we can really check that these stars were coming from the inner disk through resonance trapping and then escaped these resonances. So what I've presented till now concern essentially possibly the last some of the processes that can have been in place in the galaxy in the last 8 or 9 billion years of evolution of the galaxy, if the bar formed around redshift 1. But another, of course, hot question for Milky Way studies is what happened before. How we can describe and can we reconstruct the first 2, 3, 4 billion years of galactic evolution? And these questions is strictly related to the question of searching for the accretion events that the galaxy experienced in its early history. How to find them? So a few years ago, in the framework of the PhD thesis of Ingrid Jean-Baptiste, we ran a set of n-body simulations of a Milky Way type galaxy accreting one or several satellites. And these simulations also contained a system of globular clusters for the Milky Way progenitor and for the satellites that are here are shown as red and blue points. And one of the aim of the simulations was trying to understand whether it was possible to find accreted stars in kinematic spaces, like the so-called integral of motion spaces. The basic idea came from several works by Helmi and collaborators who were showing that if n satellites are accreted in a Milky Way type galaxy, even if after several billion years it won't be possible anymore to find these satellites as coherent structures in the sky, it should still possible to recognize them in kinematic spaces, because essentially the suggestion was energy and angular momentum can be conserved, and so clumps, each satellite will be a clump in this space, and also after several billion years it can still be recognized as a clump. Now, the problem happens if it depends strictly, the possibility to use this methodology to retrieve accretion strongly depends on the mass of the accreted satellite. And in particular, for satellites which have a mass of about 1/10 of the Milky Way at the time of the accretion, what we showed that the situation is much more complicated than that. So here you have an animation of one satellite with a mass 1 to 10 that is accreted into the Milky Way, and the distribution of stars is shown in the energy angular momentum plane. So as you see, as the satellite penetrates in the innermost region of the galaxy, stars are lost, and because the energy is not conserved because of dynamical friction, there is a redistribution between the orbital energy of the satellite and the energy that is given to the surrounding stars and to the dark matter halo. What we see is that a single satellite is able to lose stars at different energy and angular momenta, and so to produce several clumps. So the situation was, for this set of mass ratios, was much more different than that, because a single satellite was able to give rise to several structures, not only one. And I think that this work is particularly interesting now that we have to interpret the Gaia data, and you can see all the degeneracy that can be in the interpretation of these spaces. So on the left, you have the distribution of Gaia DR2 stars, and it's the energy angular momentum. It's a plot by Young et al. 2019. So here you see the famous Gaia Sausage Enceladus satellite, which is this remnant of this satellite that should have been accreted about 10 billion years ago. I will talk a little bit about it in a few minutes. And you see here also a retrograde tail of stars that has been interpreted by Young et al. As the tail of, as the remnant of another satellite, different from Gaia Sausage. And what you see on the right was one of the plots taken from the work of Ingrid, showing that a single satellite, if it's massive enough, and the mass ratio should be similar to that of the Gaia Sausage Enceladus accretion, is able to produce both a sausage-like remnant and a sequoia-like tail. So the way we interpret these spaces is not so always so easy. And this degeneracy does not concern only the field stars, but concerns also the globular cluster. Why? Because when the globular clusters are accreted, they can be lost by the satellite at different epochs of the accretion. So here you see, for example, the n-body simulations of the accretion of two different satellites with its own globular cluster system. And you see that globular clusters from one single satellite can be redistributed over essentially the whole range of energies. And on the right, you see a possible interpretation of the origin of galactic globular clusters taken from a plot by Massari et al., where different colors should correspond to globular clusters associated to different satellites. So again, the way we interpret this must be done with extreme caution, because these simulations indicate that, for example, a globular cluster in a retrograde orbit like this one can be causally connected with a globular cluster like this blue one, which is really in the deep of the potential well. So these, for example, high energy clusters here and this blue cluster here can be much more related than what we are suggesting at the moment in the literature. So overall, this comes back to the question of understanding the merger tree of our Milky Way, and in particular, try to understand how unique is the picture and the merger tree that we are currently reconstructing. So let me just spend really the last few minutes talking about the other side of the halo. So we have seen the accreted part of the halo, but numerical models for several years have shown that when massive enough satellites are accreted on a Milky Way type galaxy, the disk, the persisting disk of the Milky Way type galaxy can be heated up by the interaction. And so what the simulations were predicting is that we should expect to see a halo, a inner halo that is mostly made of heated disk stars. And this is exactly now what we find in the data. And in fact, what we did was to try to use this heating process to try to date the epoch of the end of the epoch of strong accretion into the galaxies. And so to do that, essentially, we used apogee data and we relate the kinematics of stars to the metallicity. And what we showed is that at metallicity typical of the thick disk, we see a heating of the disk. Now you see this kind of shoe-like shape with stars that are on hot halo kinematics and stars on cold disk kinematics. And the transition between these two regimes, so here there are plenty of stars which have really chemical abundances of the disk, of the thick disk, but have much hotter kinematics, and some of them are in fact counter-rotating. And using the chemical abundances of these stars, we could derive an age using the Haywood et al. Relation, essentially. And this helped us in dating the end of the strong accretion event experienced by our galaxy and place it between 9 and 11 billion years ago. So finally, the picture is complicated, but it's interesting as well as it is complicated, because on the one side, we are seeing that if we select kinematically the halo, if we define the halo kinematically at few kpc from the sun, there are plenty of stars in the halo that in fact are disk stars, heated by the interaction. If we define the halo on the basis of the metallicity, and for example, we say, what are the characteristics of the most metal poor stars in the galaxy? But there was this very surprising results by Sestito et al. Appeared last year, which shows that if we look at ultra metal poor stars below -4, about 30% of these stars, the sample are not very high, but about 30% of these, about 40 stars, if I remember correctly, are in fact have disk-like orbits, are really confined in the plane of the galaxy. So there is this ambiguity, and possible it's something that will lead us towards a new definition of also the galactic halo. And so we have been doing some work to try to relate this ultra metal poor star to the most canonical disk this year. So I will finish essentially here saying that it's of course an exciting moment, because I think already before Gaia in fact, but we are really in some sense discovering a new galaxy where the different structures are much more connected than what we were probably thinking before. And the study of each of these components requires, of course, high quality data as the one that we are now acquiring. And at the same time, it requires also models, and models that can take into account all the dynamical processes that can reshape and mix the stars over time. And of course, there are plenty of new, there will be the future Gaia releases, there will be new spectroscopic surveys that will soon see their light, and that will help in providing new data and also stimulate the community to provide the models and interpretation that can come with that. And then simply finish with something that I didn't have time to talk at all, but I think that is still very interesting, and is all we have seen for field stars. For example, all the processes that we have been learning for the bulge of the Milky Way should also be seen probably in the globular cluster population, in particular in the bulge disk population. And globular clusters can be trapped in the bar, can be also linked to partially to the boxy peanut instability. And some recent models that we run also have shown that clusters in the innermost regions of the galaxy can also interact between them. There can be mass exchange. So there are plenty of new things that I think the new data will deliver in the next future, and things to really look at in the models and in the data. And I finish here. Thanks for your attention.
Thank you very much, Paola, for this wonderful presentation. So we come back to this formal procedure. We'll first start with questions from the referees, then for the members of the jury, and then by members of the public who have HDR degrees. So let's start perhaps with the first referee, Francesca Figueras.
Okay, so thank you, Paola, for all the presentation. For the memory, it's a pleasure to read all the memory, which is extensive, a lot of information, more than the one you could present here. And thanks also for your teaching work. I think it's very hard work to teach now in a master with this galaxy that is changing. And I recognize that you are doing an excellent work in this matter. Just with the last slide, you say coming years perspective. I will just focus on two open questions that I don't know if you can answer me, because just your experience could be very good for me. One thing is that you are involved, for example, in WIF, that we know is a connection between radial velocities, Gaia, blah, blah, blah. And imagine also for most, and imagine you have some new information, vertical information, and maybe azimuthal information at the end of the galactic bar. Imagine you have new data, but maybe thousands of radial velocities in this context, in this part of the handle of the bar. Can you tell me about which is the additional information you will need? So imagine you said me the gas, the vertical, the gas dispersion can change the star formation history. Can I disentangle which are stars in the disk, stars becoming to the bar and each one orbits? How can I mix this with the gas, with information, additional information I will need? Just some future ideas of what can we learn for this small space that in fact we have near here. No? We have now at 4 or 5 kiloparsecs. We cannot go to the red clamp far away or something like that. I need some, just imagine.
The first thing that comes to my mind is related to this debate about how much do we need a thick disk to explain the bulge. So I would use probably the end of the bar to try to understand a little bit of this. And if I could look also at the vertical structure and for example, at the chemical abundances. And one of the reasons is that when we compare, as I was saying, one of the problems of all this model is, in some sense, the degeneracy. Sometimes we can use data to really constrain and exclude some models, but some other cases we can't. And if you have followed a little bit the debate between, for example, our group and Victor De Battista about how important or how necessary the thick disk should be to explain the bulge properties, you will see that the problem is that essentially you can start with very different models and end up with similar characteristics in the bulge. there are some models that are extremely degenerate. But the difference is made in what happens just outside the bulge. And so I think that, for example, the end of the bar is really a region to look at, because not all models are suggesting the same behavior. I mean, we can still have the vertical metallicity gradient in the bulge, starting with very different scenarios, but the different scenarios predict also different properties of the disk surrounding the bulge. So this end of the bar part, as we can go in and we can really relate what we see at few kpc from the sun with the bulge, this will really help in constraining. This is the first thing that comes to my mind, because it's one of the things that I've explored the most. And of course, I think that there is also all the point related to the evolution of the bar itself with time. That this super thin bar, the association of the super thin bar with the thin bar, how much this bar can be thickened over time, even if we know and we see that most of the thickening happens really in the bulge region. But what happens to this disk over time and this thin bar over time? So I think that these are things that will be possible to explore with Viv, that will be possible to explore again with Moons, because Moons will provide really this in plane study of the bar from the bulge to the end of the super thin bar. So I think that there is in some sense, I think that it will help. Yes, on the one side, to constrain this old young disk scenario, and on the other side, to really study the heating of also young population with time in the bar.
Yeah, great to bring this degeneracy. Yeah, I understand. Thank you. I have another open question. This is referred to the spiral that DR2 has discovered here very near to the sun, and then the debate that you have followed, and you have done a very important contribution, saying that maybe the buckling from the bar can produce the bending and so on. And then we end our paper saying that maybe it's a combination of both. No? Maybe it's a combination from the satellites and a combination from the disk inner instability, which is the next step. What we need from Gaia DR4? What we need just to say, yes, the contribution is this, but not this. The contribution of that, but not that. How to constrain more the evolutionary model on this complex scenario?
Well, I think in some sense, one of the things we should do, I think before, I don't want to say before even looking to the data, but I think that there is for sure an effort that must be done on the modeling part. And for example, we have seen the recent paper by Bovi and collaborators showing with the simplified, in some sense, models, that it seems that none of the parameters that they have explored for the Sagittarius in terms of mass, orbital types, is able to reproduce the strength and the characteristic of the spirals that we observe. On the other side, I think that what we have done with the buckling instability was really a first suggestion. But here to account, for example, we need still to describe how stars, and we have this information in the simulations, but how stars, for example, that are kinematically hot or kinematically cold respond to this interaction, to this bending instability, because this is the data are starting to provide this kind of information, separating in alpha pura and alpha rich, or in kinematically cold and kinematically hot. So we can now look into the data, into the simulations, and see what kind of predictions we can make for different scenarios. And then we need, I think, to have. I know that we always dream, but we need to have to explore a portion as large as possible of the disk, because a very recent, for example, interaction, a very recent perturbation can have perturbed the outer disk, but it depends when it happened. Maybe it didn't have time yet to really propagate into the inner regions. And so we need to have this large-scale view to try to understand how these spirals are mapped in terms of extension from the solar vicinity, and also in terms of response of the different populations.
Yes, but when you enlarge the area, maybe more complex will be the scenario.
Absolutely, absolutely. I mean, in some sense, I think that for the moment we cannot to be fair and to be open-minded. We have to say maybe it's a contribution of, and possibly it is a combination of different things. But at the same time, maybe from the modeling part, we will be able to really separate the imprint left by different processes. I still don't know, because we have worked only on one side, but at some point we need to couple a disk that is experienced bending instability propagating from the bulge formation epoch to, for example, satellite perturbation, and see what we get, if we get the right answer or not. So I think it has opened, this discovery has opened several years of work on the subject from all point of view.
Open questions.
Yeah.
The final one, just 1 minute. Yeah. The final one about you have a large experience in simulation, and you have gone now to the observational domain, and you have the connection. Again, your opinion about how to trace and say something more about if the spirals are transients, really our spirals are transients, just looking at the simulations and at the data. How to check and arrive to finally to say something on this context for the Milky Way. Your opinion, 2 minutes, because I understand it's late.
My opinion would be, well, something that a path that I think I would like to follow is the path that has been initiated by the work of Sergei, who I collaborated with. I didn't present it in my HDR because it was really his work, and I have not directed him in any way on this work. But it is his work to try to reconstruct the spiral structure in the disk by studying the stellar, the stars of different ages, and by using, in fact, the 6D information contained in the Gaia data. No, so the idea is to try to look to reconstruct the spiral structure, see what kind of stars, in fact, are associated with these spiral structures, their age distribution, and also their kinematic properties. And this can be a way to see how much we have to do, for example, with co-rotating spirals, how much these spirals are really transient or are more wave propagating for longer time in the disk. I think that there is a path to explore there, because in some sense we have a way to start to associate also old stars, so possibly kinematically hotter and older in terms of age, to the spiral structure. And it would be interesting to see what kind of distribution we see. And so what kind of stars are, in fact, responding to this spiral wave propagation.
Anyway, yes. Yeah. Okay. Thank you. Thank you very much. And it's all for the moment. Thank you, David, also. Thank you, Paola.
Thanks to you for reading and all the feedback.
Jessica. So we move on to the next referee, Daisuke Kawata.
Okay. Yeah, nice work, Paola. And I really enjoyed your memoir and also the talk as well. And it's very nice to see that it's a comprehensive work starting from the inner galaxy to the outer halo. So that's a great work. And yeah, I have several questions like Francesca, and I wish that I can see you and ask more questions, but I will try to ask some key questions I really want to know. So yeah, you talk about quenching of the star formation in the Milky Way in a long time ago could be due to the bar. And so that's probably related to the bar formation epoch. And then with the Sergei's collaboration, you also talk about bar buckling in recently. So is that your pictures like a bar probably formed in 10 giga ago and the buckling happened a couple of giga ago? And if so, then yeah, what kind of other consequence it may be expected? How can we check that the scenario of that bar formed quite a long time ago and then buckling starts recently?
I'm not sure that with the work on the phase spirals we intend to suggest that the buckling is recent. I mean, what we try to show is that this instability can propagate for several billion years. I think the simulation ran for 3-4 billion years, and this was essentially the end of our simulation. So one of the things that we should do is to try to really run this for longer times and to see for how long still we can see the structure. So it was not, at least in that work, a way to date the buckling instability. What we were suggesting to say is simply that the perturbation can be older than the one that was initially suggested. And that can be related to the buckling, but it's still difficult to put a limit at the buckling, also because we know from n-body models that the galaxy, that a boxy peanut bulge can undergo towards maybe more than one buckling in his evolution. So I think that one nice thing to do, maybe this it will, well, it's something that one should maybe already try to check with Apogee, but probably Mons will be ideal for that, is to try to look for signatures eventually of recent buckling in the bulge. I mean, it would be nice to find a way to try to find a way to quantify whether the galaxy, then the Milky Way bulge, had really experienced a buckling a long time ago, or there is still some sign of asymmetry or things like this that are still found in the bulge nowadays. But at the moment, what I really would like to say is that it was not a way to say that the buckling happened, I don't know, 3 or 4 billion years ago, and the bar formed 4 or 5 billion years even before. So it was simply a way to say this buckling instability can be left and can propagate for in the disk for several billion years. Now we need to put an upper limit to this propagation time scale, and also I think really to look into the bulge in situ in the bulge and see if there is any hint of possible asymmetries in the kinematic spaces, for example. But still, I think we suffer of the way the bulge, if we are looking more to the north or to the south of the bulge, it's still difficult to really put constraint, I think, on the.
That would be very interesting. Yeah, I agree. That would be very interesting to look at the kinematical stability in the inner part of the bar and see the age of the buckling, since buckling. But it's going back to that the long bar and also quenching, and so you have used the stuff chemical composition of the solar neighborhood stars to infer the quenching. Is that required? If it's coming from the bar has to be quite big to really stop affecting the star formation rate in the whole galaxy, and then it's slowing down from that. It will be quite tough. So I wonder what you think about what kind of size of the bar should be to really we should have.
and I think in some sense that we were lucky with the place of the sun, because if we were a bit farther out, probably we wouldn't have seen the quenching. And I think that we see in the quenching because even if the thick disk and the metal-rich populations are not dominant in the solar vicinity, we still have. So we still have essentially at the solar vicinity here, part of the inner disk sequence. And this is where the quenching in fact is. So we are seeing the quenching, I think, in a 1-2 kpc radius from the sun, not because initially the bar was so long to really include also the solar vicinity, or not maybe because the solar vicinity was much closer to the bar, but simply because at the solar vicinity we are able to see part the inner sequence that is typical of the inner disk. And does this answer your question? Sorry, it was related to that, so, right? Why we are seeing, how is it possible that we see a quenching also at the solar vicinity?
No, it's just the scale of the. I'm a bit surprised to think about the maybe like 8 kiloparsec bar should happen in a 10 gigawatt. But you're saying that you really don't need that big bar, but
No.
it's maybe 6 kiloparsec, 5 kiloparsec bar to stop the star formation only center.
Suppose that you have something that is happening really in the bar region. And then that because of different phenomena, for example, trapping of stars at resonances, part of these stars, for the thick disk stars in some sense is easier because they are on more elongated orbits. But some of the metal-rich stars that are typical of the inner disk, for some scenarios, the one we are exploring, other possible scenarios, can migrate to the solar vicinity. So as well as far as you can sample at the solar vicinity also the inner disk population. If this inner disk population underwent some quenching event, you would see it also at the solar vicinity.
Mm-hmm. Okay, because of the so you're talking about the migration.
Exactly. Whatever type of migration, it can be for thick disk stars, it can be also simply partially due to the fact that these orbits are eccentric, so they are exploring a large portion of the disk. For the most metal-rich part that are the end of the inner sequence, you need to provide other mechanisms, to bring them at the solar vicinity. But as far as you have part of the stars also at the solar vicinity, you can probe the quenching event. And maybe another way, the other way around to answer to this, is that when we try to reconstruct the star formation history from the alpha age relation, we were considering only stars that were selected to be, even if they were at the solar vicinity, but were selected to be inner disk stars, because we had already an idea of what the inner disk chemical sequence should have been. And what I mean by that is that if you now want to plot the alpha age relation of stars that are at the solar vicinity, but that are characteristic of the outer disk, so they are exploring the solar vicinity, but their guiding radii is higher, you will see that this sequence, this is shown in the paper, but I have not thought to report it here. But you would see that this sequence is like parallel to the thin disk sequence, but slightly offset in alpha. And you don't see in this sequence any signature of a quenching event. So again, I think we could find this quenching event at the solar vicinity because we were lucky enough to have at the solar vicinity a contamination from stars that are typical of the inner sequence.
Okay, yeah, thank you.
Yeah, and then as you move in, you really see the in situ distribution.
Yeah, sure. Okay, yeah, thanks. That makes sense. Yeah, thank you very much. That's all from me. And I hope that I can ask more questions when I meet you.
All right, thank you very much, Suke. So now we move on to the third referee, Hervé Wozniak.
Thanks. I think I must begin by saying that I have been very impressed with the quality and by the quantity of the work that has been provided for this memoir of habilitation. And I think that this work is very comprehensive, well built. We have a real focus on our galaxy. There is no dispersion on the external galaxies, I would say. And that work is very timely choice, considering the Gaia data that are arriving, and especially in view of the third release. So that's very important. I have been particularly, I particularly appreciate the fact that we can follow the reasoning very perfectly well. The red thread is very clear in this memoir. And we start from the simple to go to the complex, what we should do every time. So that's there is also another point that is about the fact that this work is obviously collaborative. That means that it has required supervision from you, I guess, so supervision of postdocs, but also from supervision of PhD students. And so on the one hand, this may seem paradoxical since we are here today to discuss your ability to supervise PhD students. But on the other hand, all this work proves that to what extent you are capable of supervising young researcher with precise scientific objectives. And I must add, in view of the results, with a clear and certain efficiency. So I think it was important to point this out here before my questions. So it's a very good memoir of HDR, I must say. So now the questions. For speaking last among the rapporteur, I have the advantage of having fewer questions to ask because most of have already been asked. So it's and many of my written questions in my report have been already answered during your presentation. So I would like just to focus on maybe a couple of very general questions. And the first one is what is, from your point of view, the status of a delicate notion of dynamical equilibrium when it comes to a galaxy like our galaxy, with the procession of satellites, the history of mergers, the history of star formation, the sign of dynamical perturbation, as we have shown, bars, spiral structure, warping, etc. So there's many structure identification techniques that are based explicitly or implicitly on the notion, on the hypothesis that there is at least locally an equilibrium. So we have to assume some equilibrium at some point. This is, for example, for the case of the inversion method, which are based on the search for a solution. And if a solution is charged on the least distance criterion, it is equivalent in many cases to searching for a solution for equilibrium, whatever this equilibrium is. So from your point of view, do we have to question the notion of equilibrium? What is the equilibrium? Is there any equilibrium in Milky Way? Do we have to change the strategy when we try to set up some new techniques to find the past history of the Milky Way, etc.? So, but what is this notion of equilibrium for you?
The notion of equilibrium, I think the first probably silly answer would be that we always need to re-question our results. So I think that, for example, from my point of view, it has been in some sense I'm much more confident, and even this I think I could re-question what I'm going to say, but I'm much more confident in trying to use models to describe the inner galaxy rather than the outskirt of the disk. And I've spent, I realized that I've spent some time a few years ago to try to implement all this Rodionov technique to have models that are very nicely at equilibrium, initial conditions that are very nicely at equilibrium, and then to think that maybe we start with something extremely different to try to. So in some sense, in fact, one of the things that I would like, that I had in mind for a long time and I didn't have time to do it yet, is to, for example, from the point of view of the n-body models, exactly to do this, to start from models that are not at equilibrium, but where we can, in some sense, control the departure from non-equilibrium. And this because I would like really to study how some of the processes that we have been studying, like, for example, radial migration, can also depend on that. I mean, how much of the results that we are finding in the models, for example, already depend on that, and how much of what we see in the galaxy can also be the result of the fact that the galaxy has been out of equilibrium for several billion years. And another clue that I think that is extremely interesting and in some sense question the notion of an equilibrium or non-equilibrium, but something that we need to add to the picture, is this, for me, this discovery of these very, very metal poor stars in disk-like orbits. Because in some sense also this is constraining, for example, how much the disk can have been perturbed over time by interactions, by accretions. We should be able to put a limit to all this, in the sense that we are not, these stars that we now find that possibly are as old as the galaxy, but they stay confined in less than 1 kpc from the galaxy midplane. Also, this can be a constraint for the amount of non-equilibrium that the galaxy has gone through its evolution. So and another point, for example, the other day I was rereading this wonderful work by Matteo Portai and collaborators on the bulge and the constraints that looking, for example, at the kinematics of stars in the bulge can give on the pattern speed of the bar. And it would be also interesting, related to what we were saying before, is the boxy peanut shape in a kind of steady state now, or did it undergo through some recent new buckling event? We don't know, but it would be also interesting to check whether this assumption of symmetries that is made in this model can, for example, impact what we get for the bar pattern speed of things like this. So I think that there are plenty of places in the galaxy where we need to re-question. Just to, not because we don't trust what we have done, but simply to see how robust some of our conclusions are to the assumption that we made in the model.
Yeah, and the point where you stop the simulation is also important, because that's it's never a real equilibrium. So that's a matter of choice and matter of observational constraint that stop the simulation. Yeah. Okay. Yeah. In fact, my last question, because as I said, I don't want to take too much time on this question. My last question is in particular with deal with the chemodynamical simulations. And these simulations require the implementation of rules to solve the physics of a few phenomena that occur under the resolution of a computed grid, so even below the space or time resolution. So among the process concerned, depending on the resolution that you adopt, of course, we find the star formation or the associated phenomena, such as the explosion of type 2 supernova, or even the explosion of Wayne A. All the energy feedback processes, the AGN, if there is an AGN in your simulation, you have to take care of the time scale that are completely different with an AGN, etc. The radiative transfer also is important in chemodynamical simulations. So all these details, well, the detail of physics is important in general. And so when one is looking for star formation quenching, for instance, I think it's quite important. So my question is, to what extent does the details of your result, of your choice, that you have made on this submesh physics influence the results that you have obtained with the chemical simulations?
It's a very good question. So in the work with Sergei, where we were simulating a full, let's say, N-body hydrodynamical simulations or controlled simulations, we didn't change the prescriptions. It means that all models were run assuming the same prescription for the star formation, for the stellar feedback, etc. So we didn't do a parameter, let's say, a sort of study because the code we used was already used several times. We adopted the standard prescription of the code, but we didn't change this prescription to see how sensitive the result is to that. While for the star formation history that I was showing related to the alpha over iron age distribution, in that case, it's a simple or complex, but only a chemical evolution model. And in that case, Owen Smith explored really a number of different inputs in the chemical model, from the IMF to the yields that were used for supernovae 2, supernovae 1a. So in that case, it really made a strong, a robust work in trying to understand whether this two-phase star formation could be found changing some of the main parameters of the chemical evolution. But I agree, and I agree with you that is something that one should always keep in mind. So we submitted a paper a few months ago where we were not even in this case, we were changing the subgrid prescription, for example, for the physics of the star formation, etc. But we were showing how it's sufficient to show to change slightly the parameters, for example, for these were models where we were starting with a hot halo of gas cooling and forming a disk, and then the star formation and chemical evolution proceeds, and we were looking at the longer term evolution of these galaxies. And what we learned is that it's sufficient to change already the halo parameters, or in terms, for example, of halo mass or halo concentration, to end up with star formation histories and chemical evolutionary paths that are not so similar from one simulation to another. So there is a problem on the way we implement the physics, and again, there is a problem in also the parameters that we are using. And so there is not, the answer is complex. Yeah. But I agree with you that we need to take into account, these things.
Especially if you change the cooling function. If you change the cooling function, especially if you take care of the metallicity of a gas in real time and compute the cooling function in real time, you can find a completely different star formation history. So that's and the bar is one more phenomenon in the complex simulations. So okay,
in these models, we are taking into account the dependency on metallicity for the cooling function, but we didn't, for example, really try, for example, to change the prescription for the when the star formation. What are the conditions, for example, for star formation? So these are things that I agree we should check.
Okay, that's my last question. I don't have any more questions. Thank you very much, Paola, for your presentation. Yeah. Thank you.
Thank you very much. We now move on to Cristina Chiappini.
Hello. Sorry, I'm here moving. Despite of my pain, my back pain, I liked a lot to read your memorial, Paola. I have some questions. I think we are all on the same boat in the Milky Way, and we know how difficult it has been to work on galactic archaeology in this last difficult and nice in these last years, with an explosion of ideas and new data and different views. So it's a very nice moment. And we, the two of us, have tried several times to discuss several of these issues. In many, we sometimes don't agree, and in others, we do agree. So that's the way the field is right now. So I'm happy that I can be here today. I read with detail your memorial, and I see that there are already several interesting questions, but I still have some. I would like to focus on the chapters to give you some feedback on the chapters. And just as a note, I think the presentation is very well organized from the way you decided to go, going towards the halo in the end. I just feel that in the beginning, the very beginning, and this is not only something that I see here, but I'm starting seeing the field. I see that you say we have already ages for thousands of stars, and that's a new era of doing things with age, and so. And I am always very careful. I mean, where are these 1,000 ages that we can trust, and ages come from where? So that is my first question to you. What do you think about how much do we know in terms of age right now?
Yeah, as you see, in some sense, I have said that we have thousands of age, but I'm still, in some sense, attached to the ages that at the moment we have Misha, in fact, measured at the solar vicinity. So when I go farther out, I try to use the chemical abundances more than ages. And if you want, one of the reasons, for example, I think you know this much better than me, the possibility to use astereosismology for ages. And at the same time, I think and I remember that, for example, if you only look at the alpha-age relation and you compare what you obtain at the solar vicinity with, for example, something that was obtained a few years ago using the first estimates coming from astereosismology in the work of, for example, I think it was Silva Aguirre, and you make a comparison between the two, you already see what the difficulty still is in this kind of comparison. So while I think that we have, I think, for example, to the works by Marie Martig a few years ago, we can start to attach ages also to stars that are not so close to our. I still think that if we want to constrain models, for example, if we want to try to run a chemical evolution model against chemical abundances age relation, we really need to use as much as possible ages that have uncertainties that are not too large. And because otherwise you can run too many different things you can be satisfied by the solution, even if the solution is not really constraining the data. So in particular, I was thinking to this debate about how thin, how dispersed or how thin is the age alpha relation that we found at the solar vicinity if we compare to other data. And I think that when we do this kind of comparison, we also to take into account the uncertainties that come with ages. And until the uncertainties are not small enough, I think it will be wise to use these ages with a certain degree of caution.
Okay. Then another point is then I would like to discuss a bit some stuff on the chapter 2. Do
you want me to take?
No, I don't need it. In some parts of chapter 2, I can just say like page 15 or 14 or page 18, I feel some of the discussions of this chapter it still would benefit of some more updating. I mean, this is a field that's going very fast, and a lot of the data that you discuss here are still based on ApoGDR13. And ApoGDR13 didn't have a good coverage on the bulge area yet. So this is a field that is developing too fast, and there's important things already in the last 2 years, as you may know. So it felt too much is still attached to Argo's discussion. And I feel sometimes that it will benefit from looking to the more recent data to get on that. On this chapter, I also would like to know a comment from you on 2 things. One is you talk in the end about the future that we're going to have in this field by using moons, which I'm also very looking forward. But I don't see any mention about SDSS-5. Would you say some word about that?
I think I can't too much, in the sense I know, being on the modeling side, for me it's easier to talk about surveys I'm following and I'm mostly involved in than to project I'm not directly in. For the what was the question for about the update? I agree. I mean, I still think that Argos and Apogee are being complementary, because they are not really providing essentially the same latitude intervals. And I agree that some of the things can be rechecked in some sense. But for example, when I look at the results that Francesca obtained a few years ago for the metallicity maps, and I compare to the recent work you have done with Keros, the work by, I think it was posted a few months ago, and I still see a very good, how can I say, the 2 seems to me indicating the same thing. When I look at the metallicity maps that you are deriving for the bulge and surrounding disk, and I compare that with the results Francesca showed 2 or 3 years ago, they seems to me in very good agreement. So while I agree with you that but the field is changing and the number of data that are arriving are so, I mean, one should revise each result every year or several times a year. But for the moment, I see that so something that I did not present at all was the comparison, because it's not published, for example, with the kinematics with the giraffe inner bulge surveys. And also there we find very good agreement. So it's something that I showed at several conferences, but we have not published it. And so I think that there is still space for this kind of models to provide a good representation of what we are observing.
Okay, thanks. Another thing that I wanted to ask you, I also didn't see a discussion a bit on the, what do you think the RR LiDARs are contributing to your views on the bulge?
I think that I think, and in some sense, this has also been shown. So at some point, it was something that I would have liked to. I started to look myself, and then I saw that there were some other very nice papers coming out, and I didn't proceed in this way. But I think that in some sense, the RR LiDAR, since because their metallicity distribution should essentially be sensitive to different populations. So I expect to find between the RR LiDAR part of the thick disk, part of the heated thick disk, part of what is the metal poor tail of the thick disk, and maybe partially something related to the accretion events. So in some sense, it's a sample that probably is an interface between different populations or populations mixing different kinematics. So when you put all this into the bulge, I expect to find possibly, but this may be difficult to discriminate, a population of RR Lyrae that is mostly responding, as I expect, a hot disk would respond to the boxy peanut bulge, while possibly there can be a hotter component also. That can be or rather associated to the heated part of the disk, or being eventually part of the accretion that ended up in the inner galaxy if these accreted stars were metal rich enough. So for me, it's a transition. It's a population. Probably it's a mixed bag of different of things that have different origins. Okay. So I think that this, yeah.
Thanks. I also would like to ask your opinion. So it's still about the bar now entering chapter 3. Because you seem to see this plume and you want to link this with something on the bar, and also the fact that this idea that this quenching the star formation, and there just a parenthesis, I can send you after, but I not so much into agree with the footnote that you have in that chapter, but anyway, it's an old discussion. The fact that you need to find a process that create a quenching, right? That could be this one is very interesting. This plots that you show for the star formation is very interesting, I find. But as you know, there is other ideas around, and these are mostly related. Some of them are related to the way the galaxies accreted gas, and therefore related to the way you treat the galaxy in the cosmological context. Mm-hmm. Given this, and that you're very much focused on non-cosmological simulation, what's your view on how the two things could help each other or cancel each other? You see, these gas flows that mm-hmm. come into different time scale into the disk.
Okay, so big question. I think that there are for sure other processes, and for example, already before even invoking, I mean, there is this gas accretion, and there is also the satellite accretions that at some point can have stimulated part of the high star formation rate that we see at high redshift. And so possibly the end of this, everything seems to happen in the same time, no? The end of the strong heating of the disk, the quenching, possibly the formation of the bar. So there can be a link between all these things. It is also possible that is related to a different way in which gas is accreted into the galaxy, and so eventually the stop of the feeding of the gas into the central region, so the star formation in the central regions. I think again that something that we should find constraint in the chemical abundances. And in fact, when we were looking for some quenching processes, what for us was important, it was that when we see the end of the formation of the thick disk and the beginning of the formation of the thin disk, and by thin disk I mean the inner thin disk, the thin disk typical of the inner disk, what we see is that there is a continuity in chemical abundances. And for us, this continuity in chemical abundances was indicating that whatever the process of quenching is, must be possible a process that does not imply a large reservoir of gas with a different chemistry providing the fuel for the star formation. So the idea that we were following was that essentially what is changing between the star formation in the thick disk phase and in the thin disk phase is not that the gas was most consumed in the thick disk, and this is why the star formation rate decreases, but that possibly the gas that was still a large amount of gas sitting somewhere in the galaxy, but this gas was not forming stars efficiently enough. So I don't know if this answers to your question, but in some sense, to me, this chemical continuity that we see should provide also some constraint about what happens. Are we changing drastically or substantially the reservoir of gas that then form the stars in the inner galaxy, in the thin disk phase, or not? To me, the answer is not. So whatever is providing the evolution of the and the formation of the thin disk in the inner galaxy is strictly is coming from an ISM that, in terms of chemical properties, is similar to what we had at the end of the thick disk phase. Another story is what we see in the, let's say, in the outer disk. And there, yes, we need some kind of dilution, whatever it comes. It's related to satellite accretion. It's independent on it. It's gas raining back from the hot corona. I still don't know. I think that there are several possibilities. But to me, a way to constrain, and also so to constrain cosmological models, is really to look at this continuity or non-continuity that we can see in chemical abundances, waiting for ages.
Okay, I would like also to call attention for another point that in your presentation and the way you spoke, and also the way you wrote, there's this notion of the inner disk sequence. And the inner disk sequence and the non-dichotomy there, and anyway, this that you just said again. I think this is something that you also should open up a bit, because you are looking at the Hayden plot still, and this is 2013, as I said. And the Queiroz et al. Paper on the first one, not on the bulge, but the one, the whole disk, which is out since 2019, December. And in the AstroPH, really shows that these things change, because when you have now more data, you see that this double sequence that before we thought we were seeing only in the solar vicinity is actually seen all the way towards the inner part. So you have this double sequence all the time. So in this sense, I think we need really to be open and how we're gonna interpret this. And then it comes into the bulge thing and the bar. So giving all this complexity, I ask myself, and do you believe that let's suppose if you go to detect some stars in the bar and you measure their ages, do you believe this gives you an age of the bar, or doesn't give you any information because you have a lot of bar trapping? What would you do if you had a full bar with ages? What would be your taking on that?
Full bar with ages. So the first thing to take into account usually is that there is a difference between the age of stars that can be found in the bar or in a boxy peanut bulge, and the epoch of formation of the structure, no? Because of course you can form a structure, for example, 8 billion years ago, and you will probably stars of all, at least all stars older than 8 billion years will be in different amounts, but trapped and contribute to this bar. So if I measure old ages, it does not necessarily mean that this is providing the age of the bar. I think that if I had the age of all possible ages of stars in the bulge, what I would like to see is to what extent we find also contamination from younger stars, and how many of them, because there are now possible different works that have pointed out to the possibility that there is also a fraction of younger, and by younger I mean younger than 8 billion years in the bulge. And so this would be interesting from the dynamical point of view, because it tells us also something about the ability of the bar and the boxy peanut bulge to keep trapping newly formed stars in the resonances, and so possibly it can provide some indication about the evolution of the strength of these asymmetries with time. And then I would like to see how much this is consistent with, for example, a scenario where most of the bulge is made of disk stars. Modulo the fact that in the bulge we see, if the bulge is mostly made of disk stars, of course the redistribution of the ages in the bulge at a given latitude will be different to what we see in the disk, because the boxy peanut is reshaping all this disk material. But I would like to see whether the two are consistent. For example, age metallicity relations, possibly alpha over iron age relations, and so on. I think that this would be something interesting to look at.
Okay, I have just one last question, if I may, is related to chapter 5. And the chapter 5 is on this idea. You're kind of pursuing this idea that the thick disk is always there for whatever subject you are on it. Yes. So to end up with this again in the globular cluster thing, where you really would like that these clusters are thick disk.
I'm the last of a series. I don't want to say.
Okay. And I feel that the figures that you discuss in that chapter, the one that you say, oh, there is much more agreement now between thick disk with this scale length than before, if you look to the data of the distribution of this density. And I see that figure, I think it's 5.4. I don't see such a good agreement, I would say, in any of the cases. But anyway, this is discussable, and this is a difficult one because this is a more general figure. But then I look to 5.5, where you have this clear chemical difference, and you say, oh, but there are shifts in this chemistry, and sometimes they can look overabundant with respect to the thick disk, and therefore they really look like something else. But it could be also the measurements that are problematic, although the figure is beautiful. So this is something that I'm a bit worried, because, for example, there is a whole discussion on this issue, on how much these shifts matter, and is the thick disk and the bulge really with the same chemical pattern or not? This is a discussion that is in the review of the bulge of Beatrice Barboui from 2018. There is a whole discussion about that. There is a whole discussion of the impact of the young population in the bulge. And so I feel this chapter, of course, I understand this is an ongoing work, as you said, it's based on a thesis that's not published yet. But what do you see? So you want to find that figure that you put. You don't believe it, so you believe that this is systematics shift.
I'm worried. So just to give you briefly the history, this is a work that now dates back to, so the thesis was defended in 2017, 2016. So this was the first part of the PhD work, so it must date back to 2014. So it's not anymore an ongoing work in the way it is presented here, because as I said, there are new data that we need that we can compare these. So we need to remake the analysis, okay? And this is why essentially it's given here, but it has not been published yet. And a figure that I didn't show here, but is shown in Ingrid's thesis, and I can send you later on if you want, is that there is for sure a problem of systematics. And the reason is that Ingrid then went to look for other works that were not included in the Carretta et al. Compilation, and looking for specific clusters to other estimates of the alpha over iron abundances, finding significant different results. So depending on the data we were using, we could see that some clusters were off of 0.1, 0.15 dex from the thick disk relation, or could be on the thick disk relation. We were talking about same clusters, but simply different measurements of the different estimates of the alpha hour iron abundances coming from different works. So this is where I thought that that all the discussion that was made about the distribution, the spatial distribution of clusters, and the fact that, because what we had in mind and what motivated the beginning of this work was this Minniti et al. Idea, that Minniti idea, sorry, it was, I think it was the only author of this paper, where he essentially was saying this population cannot be a thick disk population, the globular cluster, as it was suggested before, because the scale length that we derive from the globular cluster population is larger, significantly larger than the scale length of the thick disk population, as we knew it in the 90s. Now, this thick disk population, the scale length of the alpha abundant thick disk population has been significantly revisited. So I think that this is the reason, this is one of the things that motivated the beginning of this work. And I still think that the part that concerns the spatial distribution, modulo the fact that now we have new data on the distances of all these clusters, so we need to recome back to that. It's much more robust than the part on the abundances. But for me, the worry is on the data. I don't want necessarily to put all the thick disk, all the globular clusters in the inner galaxy on the thick disk. I like the thick disk, but it's not the aim of the work. But at the same time, we have seen that systematics have affected also the way we have interpreted the metal population in the bulge for a long time. For a long time, we have seen differences analyzing the chemical abundances of giants in the bulge and comparing that with chemical abundances of dwarf stars at the solar vicinity. And we see how these differences, even if some differences can still be present in the data, they are not at all at the level we were seeing that a few years ago. So I think it's important to understand to what extent these two things are really different. And given the data that I present in figure 5.5, to me, it was really different. And in fact, this is one of the reasons why we were pushing to observe these globular clusters with moons. Because at this point, we will have the same instrument observing globular clusters, field stars, the same reduction pipeline. So at some point, we should start to reduce some of the systematics. And so at this point, I will possibly be able in a few years to tell you these things really look the same or not. Here, there is really some difference between the globular cluster and the thick disk population.
Okay, I thank you a lot. I don't have any more questions. I passed my time, and yes, as just a suggestion, keep it open. I mean, the data is coming, and we have to be able to revise our ideas without.
Absolutely.
Yeah. Okay. Thank you.
Thank you, Cristina.
Thank you, Cristina. We now move on to the next member of the jury, Vanessa Hill.
Hey, thanks a lot, Paola, for this beautiful presentation. And I have to say that, like all the other people on the jury, I really appreciated the document that you submitted before. And in particular, I think that's it is a very nice reference for newcomers to the field to have a complete idea of many of the different open questions and the last few years advances on a number of these questions. And I really appreciate the way and the care that you took of really writing the whole thing up as a complete document rather than just sticking papers together like a lot of us do for HDRs. So thanks a lot for this, Paola. I cannot let this defense finish without talking a little bit about some of my latest fancies, and those are the metropole stars that seems to be occupying orbits and location in the galaxy that looks like a disk. So just taking one small step back, I think that the work that you've put together to show how the different flavors of the galactic disks rearrange themselves in the central parts of the galaxy to make what we call the bulge or the boxy peanut in the center of the galaxy. And so my question is really, I mean, in this particular context, what do you expect to see in terms of the inner parts counterpart of that disky metal pore population?
I would expect to find both. In the sense, I would expect that the very metal pore population that is associated to the disk should be mapped into the bulge as essentially the thick disk. So as essentially the old part of the thick disk, let's say as stars of the thick disk with metallicities between -0.5 and -1, essentially the C component if we want to stay in the Argos nomenclature. So I think that the ultra metal poor, very metal poor stars that are associated to the disk, if they have a counterpart in the bulge, and I think they have, should show characteristics similar to component C. And then there is the other part of the very metal poor population that can be related to accretion events, or can have been heated to even hotter kinematics, and this is possibly more associated to the kinematics of components D or E if we want to stay in the Argos nomenclature. So there should be essentially a population that is colder, and so that in the bulge also would appear with characteristic of a colder kinematics, and this is the disk part of the metal poor regime, and then a hotter population that possibly do not show any signature of a peanut. Now, these are in the ideal world where we are really able to have a sufficient statistic for these very metal poor stars and ultra metal poor stars to be able to trace the different components. I think that we would find the two. That is something that you don't have in the two, or possibly a continuity between the two. But I mean, we should have essentially, the solution should be bracketed by the response of a disk as the metal poor disk of the galaxy and the hot halo component. And yes.
Yeah, perhaps I can also guide a bit the debate by so you probably saw the latest work by Anke Arensen showing the kinematics of the basically extending what we know for the more metal rich populations into a regime that can be really cold by, I would say, non-bulge aficionados as real metal poor stars. In the bulge, and so you know that for now I think that this metal poor population is still quite elusive in the galactic bulge, so that we do not have let's say a full census of what are the orbits that they occupy, or even a complete let's say density mapping of where they are. But there are still already some indication from the kinematics that they seem to be indeed continuing the lower rotation pattern with metallicity down to very low metallicities. And so is this not ruling out that there is a substantial fraction of the metal poor disk being there?
So let's say that until now, I think that looking at different works, the work by Federico, the work that we did slightly higher metallicity, the work of Cordoni, we all end up saying that between 20 and 30% of these very metal poor stars should be on disk orbit, despite we are using different samples, etc. So if we look now in the bulge, and if the proportions are similar, we should expect that about 1/3 of these very metal poor stars could be originally stars coming from the disk. Now, the problem is to find a way to separate them, in the sense that if we take all the very metal poor population, and we derive, for example, kinematic relations for this, we will be for sure, we will suffer of the contamination from very metal poor stars, but which initially had more halo-like kinematics. So we need to find a way to separate stars that at similar metallicities at possible different origins. So we need to decouple the two. I don't know. So on average, we can still have something that at some point is more flattened than what we see for the more metal-rich population, but this can hide differences. And I thought that in some sense, the works that you were citing were going the direction also to suggest that it's possible that there is also a disk population taken into the boxy peanut instability also in these regions. But I think that the difficulty will be there, no? The difficulty to have things that maybe from an abundance point of view are very similar, but that can hide difference in kinematics or in a spatial distribution.
And perhaps following on the same line of thought, but looking the other way around in the galaxy. So, I mean, in all of this line of thoughts that you've been developing, where the inner disk is a bit has an evolution that is a bit independent from what happens in the outer disk. What would you expect for this primitive disk metal poor population in the outskirts of the galaxy? Would you predict that you find none? Would you predict that you find
let's say like this, now also this very metal poor population can be a combination of things, no? And as we have said, there is not only us, but as we essentially all are suggesting is that a mix probably of stars formed in situ, stars accreted, etc. For the population that formed in situ and that seems to share properties similar to the thick disk, to the canonical thick disk, I would expect this population to have the same spatial extension of the thick disk. So, so I expect that part of this very metal poor population has an extension that does not go far beyond the 10 kpc, as we find for the canonical thick disk. That said, this can be the part, the beginning of the formation of the inner disk of our galaxy, but still we have to understand the origin of the outer disk. And so I don't know how low in metallicity we can go and what is the origin of this metallicity. I cannot exclude that there is, for example, if we look at the low alpha sequence, the low alpha accreted sequence, we also see that part of this low alpha accreted stars that we still interpret as accreted stars are on disk-like orbits, very extended, but part of them are on disk-like orbits. This was already shown by Nissen and Schuster in 2010. So is there a very metal poor counterparts of these stars? I don't know. But for the very metal poor stars that can be associated with the thick disk, I expect to find that confined in the same region that is occupied by the canonical thick disk. And I think that some indications already, if one looks at the orbits by Federico, those that are, and also to the one that we showed for more metal-rich stars, I think that these that are on disk-like orbits are very well confined. I don't remember cases where these stars have orbits very radially extended. But you see, I mean, you can follow a population, but maybe you have several other ones that are mixing confusing the signal. So it will be challenging to separate all these things.
Thanks. David, may I have a last question or am I over?
Yes, of course, you can.
Thank you. Then I think it will be quite quick. So it's on the last parts of your document that you had to go quite fast in your presentation. So on the simulations of the globular cluster systems, so you show that in the inner parts of the galaxy, you expect to have significant probabilities for encounters of various sorts between the clusters, and that this can give rise to some of what we've known for quite a while already of clusters that have multiple populations. And so my question is, I mean, should there be any remaining traces of the proportion of clusters that do show multiple population as a function of their location in the galaxy, or as a function of their kinematics? What is your prediction on this?
Yes, I still cannot give you strong prediction on this, and the reason is the following, that I think, in some sense, I think that this work, whatever we will find in the data, it will be interesting in a way or in another, in the sense that we were saying, if we have enough cluster in the inner disk at early times, and if these clusters were massive enough, we expect to have n mergers or to have a certain amount of contamination. So if we don't see this in the data, except for the Tarzan 5 case, that I think it would be the one that can be explained in this kind of scenario. But if we don't see many more cases where we can, for example, see contamination in the outskirts of clusters from stars that are completely different in terms of chemical abundances, for example, I think it will be a way on the long term to constrain the initial conditions of the globular cluster systems in terms of number of clusters in the disk at early times. Now, what is the problem is that this simulation was run in a kind of ideal case, as we always start, where we have a population of globular clusters in a disk already formed, and nothing else happens. But the point is that we can expect that at least at some point, this disk population of globular clusters has gone through the same dynamical processes that have been experienced by the disk. So part of this population has been probably heated by the accretion of satellites, and in fact we saw this in the simulation by Ingrid. So we had some disk clusters that are expelled in the halo, and this has been found also in the works by Florent Reynaud, for example. I mean, it has been discussed in several works. So this means that once this population puff up, the probability to have mergers and flybys and the mass exchange will diminish because the volume will be increasing. So you see that it's not that simple to attach a final number to these things. But I still think that if we don't find any of this evidence in the clusters, in particular pollution in the outskirts of clusters, that will be difficult, of course, to probe also with moons. But if we are able to find some of these things, we can put constraint on the density, number density of clusters that we have. That I think it's a completely open question, because how many globular clusters were in the galaxy 13 or 10 billion years ago, we don't know. So we started with a systems of 100, thinking that part of this system has been dispersed, destroyed, and part is now part of the inner halo. But it will be. So I think that in both cases, even if we don't find a positive answer in the sense we see this contamination, this mass exchange in the cluster themselves, I think that if we don't find anything, this also will help.
Thanks a lot. I think I need to stop here because time is going by. Thanks for everything, Paola.
Thanks, Vanessa.
Thank you, Vanessa. Now we move on to the last but not the least member of the jury, Rodrigo Bata.
Hi, Paola, and that was a really lovely talk and a lovely memoir. And I just wanted to congratulate you on this amazing work you've done over the years, really, which has taken a fairly, just a holistic view of the Milky Way, and from the point of view of the modeling to trying to analyze the observations. You've just shown tremendous scope and range in this work. So really congratulations on all of that. And yeah, so Hervé complained about having his questions already asked early on, and it's getting even worse. I've been sort of crossing them out because they've many of the issues I wanted to bring up have been mentioned. But I wanted to bounce off perhaps first about one of the things that you brought up in your talk, and I was just wondering, can you think of a sensible way to define, say, the halo? Given everything that goes on, right? I mean, do you think we're sort of getting towards the end of this sort of component view of the Milky Way, given, your work has been showing that a lot of this stuff gets mixed up, or do you think it's still got lots of mileage?
I think it will be, starting with the difficulty that we are overall all having now in attaching anyway a nomenclature to what we are talking. All the nomenclature about the Milky Way is becoming very difficult. But I think that the halo will be one of the things that will probably, in some sense, we will need at some point to redefine the halo. And the first thing is that, as I was saying, when we look at some KPC from the sun, and we describe the halo, we cannot imagine, I think, anymore the halo without thinking about the contribution of the heated disk to the halo. Now, this is a view at few KPC from the sun. So we can expect that once we start to enlarge this volume, we will see more and more the contribution of accreted stars increasing with respect to the heated disk. And for a long time, we have been thinking that when we define the halo kinematically, in some sense, we are defining also in terms of metallicity. That is, most metal-poor stars tend to have hotter orbits. And this is still true, but then we see that in fact not all have these hotter orbits. So, I think we can still keep in define the halo in terms of kinematics and in terms of overall morphology, distribution, extension, and this is one thing. But probably we will have at some point to decouple this definition from the search of the first stars formed in the galaxy. And I think that this is where I possibly see the tension between, and this is also what for me is difficult to present to a student. We keep saying students, in some sense, it's super interesting to study the halo because it contains all the signatures of the accretion events, but also because the first stars in the galaxy formed in the halo. And at some point, maybe there is some tension that we will have to clarify, but probably still too early to clarify it now. But I think that we will keep having some ambiguity in the way we talk about the halo and what we really mean by halo. So we should need the same care that we are starting to apply to the disk, talking in terms of alpha-enhanced thick disk that is not alpha-enhanced, etc., etc. So I think we will go through the same difficulties with the halo.
Oh, thank you very much. So from a completely selfish point of view, I've been I'm really interested in your answer to this question. How close are we, do you think, to understanding the survival rate of globular clusters in the bulge? And I ask this because I think we're finding lots and lots and lots of remnants of streams in that region. And from a technical point of view, is this something that is going to be tractable to sort of figure out whether what the initial population was?
Again, I think there are some difficulties that are associated to the evolution of the underlying Milky Way potential. That for sure has an effect. the only fact at some point to take into account that in inner galaxy there is a bar. What are the consequences of all these clusters trapped into the bar on the mass loss from the cluster, etc. And so one difficulty is related to the fact that the Milky Way potential and mass distribution is changing with time. That is something that, for example, in these models we are not taking into account at all. And the second difficulty is on the initial conditions of these globular clusters. And there, I think we are still, for the moment, we are in some sense very related to assigning as initial conditions to these clusters what we know today about these clusters. And for me personally, it's difficult, that probably simply because of a lack of knowledge on what these globular clusters should look like at the time of their formation. So how we can implement this kind of physics and conditions into the models. And I think that this will make the difference, because we often start with clusters that are already very dense, and this will affect the tidal effects, the disruption rate, etc. While
the population's properties as well, exactly. I'm shocked to find out that they really do have a big effect, right?
Exactly.
There's this huge parameter space, yeah, for sure.
Exactly. While, for example, this increase in density can be also the result of a long-term evolution of these clusters. So maybe only the densest survived in the central regions, and so there can be an overall. And so in this case, maybe we don't have to look at clusters, but to look to the field stars. No, all these works that have been, for example, initiated with Bulge, I'm thinking by the work led by Riccardo Schiavon, where they were looking for stars in the field that had properties and anticorrelation similar to what we find in the bulge. So maybe we should look into the field to see how many stars can be reasonably associated to stars that escaped at some point from globular clusters, to try to reconstruct what was the disruption rate. So how much these clusters contributed to the field. I don't know, I think it's difficult. So in some sense, these models are still very, very preliminary and simple, also because sometimes to understand difficult things, we have to start simple. And but there are many parameters, yes. As you say, there are many parameters.
So once the pandemic is over, I'd love to come over and ask you loads of other questions, but just one final thing, just to, what's your vision beyond Gaia? Have you thought that far into the future? It's easy, right?
Yes and no. In the sense, yes, I've thought about it. At some point, I tell to myself, well, until a few years ago, we were still working on Hipparcos data and finding still new results using Hipparcos data. So I think that the long term, what Gaia is providing us, will really help research for I think several decades from now. To me, what will be really interesting is to couple, but because for example, all the studies the studies that we did on the halo, where we were showing that essentially kinematics alone is not really sufficient to try to reconstruct the accretion history of the galaxy. So what I would really like to have is to have spectroscopy and chemical abundances to associate to these stars for as many stars as possible. So in some sense, MSO in this sense would be, I think, a fantastic tool to enlarge all these volumes. And but also to take into account that possibly we need really the next generation of these spectroscopic surveys should try to push as much as possible decrease as much as possible the uncertainties that we have on chemical abundances, because at some point we are at the point where where we cannot recognize eventually, we cannot robustly say if two groups of stars originate from two different satellites on the basis of their kinematics, but we cannot at present even say that on the basis of their chemical abundances. I mean, the law, what we call the law alpha sequence, can be in fact several satellites, not necessarily one, and maybe it's not only an accreted sequence. And I think that to try to really push further the studies, we also need to push further the precision that we can have on the chemical abundances.
Well, thank you very much, and congratulations again for this lovely work.
Thank you. Well, I also have a few questions, quick ones. So perhaps in the interest of time, short answers, please, Paola. So yes. First of all, again, I would like to congratulate you for the manuscript. I've read all these chapters for the inner to the outer galaxy, and I realized I missed many references. So for me, it has been really illuminating. And also your presentation was really clean and very, very pedagogical. So congratulations again. So I have only three quick questions. The first one deals with the P-knot in the bulge. I'm interested in the orientation of the P-knot. The reason being that the microlensing events are due to self-lensing in the bulge. And the question that arises is whether the angle is small enough that this self-lensing will be strong enough to account for all the events which have been observed. So there was a controversy back in the 90s whether the angle was something like 20 degrees, in which case you can account for basically all the events, or rather something like 37 degrees as I've seen recently. So I was wondering whether you have been using kinematical data, so all the radial velocities, but also how constraining are the proper motions of Gaia for the bulge context?
So I've not worked myself on the orientation of the bar, except that when I have to cite what is the orientation of the bar, I really trust all the work that has been done by Chris Wegg, Ortwin Gerhardt, and collaborators. But in principle you can, and in fact, for example, in n-body simulations, when you want to, if you want to take an n-body model and to compare with the kinematic maps of the bulge, you need to orient your simulation and the bar in a given way to be able to reproduce the kinematic features that you observe, and you end up with values that are similar to the one that are provided in the literature. So I have never tried myself to find the best orientation of the bar comparing the models with the data, but you see clearly in the models that you need orientations that are compatible with the one provided in the literature to be able to reproduce the data.
And presumably the proper motions from Gaia will lift some of the degeneracy.
Yeah, and indeed there are already some works that came out, I think, a couple of weeks ago. For example, coupling the Argos surveys again with proper motions for Gaia and making a study of all the characteristics of the kinematics in the bulge. So for sure, this work there will provide a supplementary constraint.
Okay. Thank you. Now, moving from chapter 2 to chapter 5, I've been very impressed by these, again, simulations of these globular clusters. But I was wondering whether it would be interesting to actually embed them into dark matter halos. Because, you know, it would be very unlikely that these objects with 10 to the 5, 10 to the 6 solar masses are not dark matter dominated. In which case, you know, the dynamical friction, the mass loss rates, everything will change. And I think now that Alessandra is joining your group, I think there will be an ideal opportunity to actually make a more realistic simulation of this system of inner globular clusters. The argument that globular clusters have no dark matter is nonsense, right? I mean, from a lambda CDM point of view, this cannot happen. And second, the absence of evidence is not evidence for absence. And so it's obvious that globular clusters are probably the remnants of the nuclei of dwarf galaxies, or the very first objects to be formed after recombination. So they must be dark matter dominated. Whether the M/L ratio is 10 or 100, that's another debate. But I think it will be really interesting to look at the inner system with dark matter.
This is a very good suggestion we can explore. So in some sense, it comes back to one of the answers to Rodrigo on that we are modeling the clusters as we know them today, but possibly the initial conditions should be significantly different. So it would be a very nice other option to explore. Yeah.
And my last question then is on these models of the galaxy. To use one of your sentences in the introduction, do you think these models are kalos or agathos or both or neither?
No, for me, kalos, chi-agathos is too high for any n-body model or chemodynamical model. But I think it's, in some sense, what I like of all this work. Of course, there is a lot of me, no? So it's partly my own work, in part the work of my collaborators. So it's clear that I like it. But if I have to find the beauty in this work, in some sense, is the simplicity of the model we are starting from. That for me, it's really important because it's important for me to understand. When I have too many parameters at the same time, I start to be lost. And so probably they are too simple, but it's a way for me to complexify things with time. So yes, so maybe there is some kalos and some agathos, but it's not yet at the Greek, ancient Greek level. Yeah.
Okay, thank you very much. Now I should ask Gilles whether are the members of the public who hold HDR willing to ask any questions to Paola? Gilles? Gilles, are you around? Okay, it doesn't seem to be.
No, maybe.
So what? Okay.
Maybe.
I checked. I don't see any questions on the YouTube channel.
All right. Thank you, Vanessa.
Thanks.
So perhaps we are. The jury is going to convene in a meeting room, and then we will be back after our decision is taken in a few, about 10 minutes or so.
So I will stay here. Huh?
Right.
Wait, can I just ask where is the other meeting room link? Sorry for that.
It's at the bottom of your screen.
To the right of record.
Next to what? Sorry. Next to recording.
Yeah, but the thing is, how can we join them?
Join break room. Ah, okay. Yeah, okay.
Usually you click, you should click on that and you should be.
Okay.
Yeah.
Will do.
Je sais pas, mais ça marche pas avec moi.
Oui. Oh yes.
Ah oui.
Gilles, merci pour avoir attendu. Ah. Non, mais Vanessa dit qu'il n'y en avait pas, donc